Hi, this is Jia Xiang from Cornell. Today I'm going to talk about ΔYNAMICS, which is my internship project at Amazon last summer. The quest is to ask, how can we perceive and represent real-world rigid body dynamics? For example, given a video like this, we want to know its velocities, position, shape, camera pose, or its physics. It is not an easy task, and my work is focusing on estimating all these parameters in one shot, but also make it executable and simulatable in the physics engine. There are a lot of previous work on this domain. However, they are mostly focused on fixed number of objects or non-camera pose. In this work, we're trying to figure out a language-based representation, such that it can generalize towards various number of objects and diverse camera poses. The choice of language is using the monocular, which is a physics simulation engine that is widely used in robotics and reinforcement learning. Here's our problem formulation. Given video, our model generates a parameter set in text format, and then it is going to be executed with monocular to get a reconstruction. The parameters that we consider including three primitive shapes like spheres, cylinders, and boxes. And then we focus on rolling and sliding friction and damping coefficient. We also have the 3D positions and velocities, the quaternion, but also the camera pose like height, pitch angle, and field of motion, view. And finally, gravity, which serves like place speed parameters. So the model is going to generate a configuration like this, which is in a YAML format. However, there's more we can do with VLM. So there are basically a lot of events that occurs in one video. And think about this. If a model can generate sentences like, a box stops moving at a specific time, it possibly means that it has a stronger visual understanding. So here's the way we do it. With traces and artifacts, we devise some event mining script, and then we make it a motion reasoning text. So now the model is going to generate some reasoning text before it generates the final prediction, the configuration. So here's the general pipeline. First, we train two models, one with reasoning and one without. And then during training time, we sample a lot of scene configuration, synthesize the video, and we generate the audio flow with Repre model. And then our model is going to generate the predicted configuration. We use an NLP objective to fine-tune the model. And we do a similar thing during evaluation. During training, we use 400K musical simulations with 10 RGB or audio flow frames as input that is uniformly sampled for 1 second video. We use the Qwen2.5-VL-7B as a base model. For baselines, we consider non-VLM baselines, and the VLM baseline that is induced with in-context learning. The result shows that audio flow as an input modality did perform better than RGB because audio flow is more semantics invariant. We also show that motion reasoning did improve the accuracy, the IOU, and audio flow endpoint error. Addition to that, we also show the cross-engine generalization. Since we trained the model on monocular engine data, we tested it on Blender dataset, which is CLEVRER. And it shows that the model did perform pretty well on CLEVRER without further fine-tuning or post-training. We also evaluate our model on real-world evaluations. For example, on boxes collision, on cylinder collision, or on both simulation. Here's more results on cross-primitive shape interactions. And this is my favorite, the massage roller bumping. Also, the irregular shapes. And it is pretty hard because basically it is hard to capture its full trajectory with a primitive shape like just cylinder or balls. And also the multi-object interactions like multiple tissue boxes and pool balls. We also try to estimate it on the self-driving car scenario. However, due to a very large gap between the synthetic datasets during training and the inference time, the model is not performing the best. However, we still see some emergence capabilities in capturing and estimating and represent some slight motions. In summary, we identify a language-based representation for motion dynamics, and then we propose to use VLM for rigid body physics inference. Thank you for listening.